Okay, let's start again. So we had random walks and we learned diffusion equation and we learned various properties of random walks. Okay, and then we sort of switched to population walks. And then, we use this simple argument that let's think of a population that is changing over time, and then think of it being in space. Okay, and then we thought of space as a grid where each grid follows the well-known logistic model, meaning the populations are driven basically by intraspecific competition, right? So for each location X, we said that the logistic model is true. And then we said the movement between grids can be approximated by random walk. Therefore, we wrote this equation for how population spreads in space. So the spreading is via diffusion, whereas the birth and death happen via what we call a reaction term. Okay, the name reaction sort of comes from chemical reactions. In this case for us, it's the birth and death processes. Okay, that causes the reaction term, and the spread causes the diffusion term. But of course, we can write this in 2 dimensions also, right? So x, y, t is the only thing that changes between the equation above and the equation below really is the fact that I'm now writing 2 arguments. I'll just write that for sake of completeness. Okay, and you could generalize this to any dimension. Of course, the diffusion term will in turn now have 2 terms. Okay, so I'll write that below here. Plus diffusion in the x-axis plus diffusion in the y-axis. Okay, and when I'm writing an equation like this, I'm assuming that the space is isotropic, which means it is same in all directions, both the directions. If the diffusion constant is same in both the directions, so therefore I have a common diffusion constant d. Okay, and we can also write the same equation in polar coordinates. Let me not go there right away. So we have this diffusion equation 2 dimensions now. Okay, so now last time we also sort of revised the idea of mean field equilibrium, which is what we basically studied in the entire previous semester course, mean field equilibrium and stability. Okay, so now we do know that for the logistic model, we know the equilibrium and stability, right? Let's assume the case where R is greater than 0, and of course the carrying capacity is greater than 0, right? So what we have is there are 2 equilibrium. N star is equal to 0, which is unstable. Okay, and we also have N star is equal to K, which is stable. Okay, this is something we already know. So now we can ask, what about the spatial model? What about the spatial model? Now we have in the spatial model, we have space. I cannot talk about just equilibrium in the same sense. So we discussed the notion of homogeneous equilibrium. Is the spelling correct? Homogeneous, or maybe there is no need for you. Homogeneous. What does it mean? Consider a scenario where every grid point. So let's write this on the side here for a cartoon picture of space. Okay, so I can divide the entire space into sort of square grids. Okay, pretty bad picture as always by me. Okay, okay, now so we can consider this at some time t is equal to, let's say, K for all x at some given time t0, let us say, it's equal to k, that's the same carrying capacity. That's one possibility. What happens in such a case if the value of population size is same at every location, if the density is same at every location, what happens to this term, diffusion term now? This will be 0 because everywhere it is same along space. Therefore, the very first derivative of population density with x will be 0. Therefore, so will the second density be, right? And even this will be 0 if we had a two-dimensional world. Okay, so therefore, if you look at this now, right? So we have the reaction term, right? Nxt by k plus the diffusion term. This now has become 0. What about this term? Because we have said that this is equal to k for all x, now this term too becomes 0 for all x. So clearly the entire left-hand side is 0, right? So this implies that if we take the mean field equilibrium and consider the homogeneous version of it, that is indeed an equilibrium, right? So n star is equal to nx, which is equal to k for all x, is an equilibrium in the spatial model. Of course, we can generalize this. We take any model of this form, okay, where delta square is basically okay, just think of two dimensions. Okay, so this is just a shorthand notation for writing two partial derivatives in space. Okay, and of course, it's just generally extendable to three dimensions as well. Okay, this is a thing that happens occasionally. I have no clue why this happens. Suddenly, this is floating around now, right? Now, once this happens, anything I do begins to float. Okay, the only thing I can now do is just only thing I think that works is I have to quit this and restart. Okay. If any of you know why this happens and how I can avoid, please let me know. It really helps. If there is some button I might be pressing without knowing, that was probably the cause, and I hope should I undo it, I have no idea. Okay, so consider this general equation. Now consider the mean field equilibrium. How are they all given by? They're all given by n star, where f of n star is 0, right? Now consider the following homogeneous equilibrium, which is given by nx is given by n star for all x. So x could be a vector here, need not be a scalar. Is is indeed an homogeneous equilibrium solution of the reaction diffusion equation. So do all of you agree with this? Do you have any questions? So this n star can have many values, right? 0 k in the case of logistic model. It could be 0 nc and k in the alley effect model we discussed last time. It could be even more. Think of harvesting model that we have studied in the previous course. It could be 4 equilibrium. So as many equilibrium there might be, but if you take any one of them, and if you set the entire space the same value, that will be an equilibrium. Do all of you agree with this? So homogeneous, one can maybe let's call this homogeneous equilibrium with where we set each location value is equal to one of the mean field equilibrium. Of course, every location must have the same mean field equilibrium. Okay, that then becomes an equilibrium for the reaction diffusion equation. Okay. Any questions on that? Do you agree with that point? Okay. So what do we do after having said equilibrium? The next thing we study is stability. We can ask the following question. Are not all do homogeneous equilibrium as defined above, right? Have same stability as their mean field model. So what exactly do I mean by that? Now again, take an example of the logistic model again, okay? Okay, logistic model with diffusion. Let's now take n star, n of x is equal to 0 for all x. We know that n star is equal to 0 is unstable, right? In the mean field model. Right? So the question is it unstable in the above reaction diffusion equation? And of course, I can ask the same question for n star is equal to 0. We can ask. The same question for this. For all x, is this stable in the in reaction diffusion equation? Can somebody guess? What do you think? Any reasonable guess?
They should be like the same case as.
We should have the same stable structure as the mean field model. That's one possibility. What is your argument for that?
So, so even if we say somehow perturb the system, so each individual block will try to attain its carrying capacity, and in turn there will be diffusion along the complete square.
Okay. So let me try to present your argument using my horrible cartoon skills, horrible drawing skills. What you're saying is, let's say that there is one grid there. Let's say everywhere we have 0, right? Let's say zero equilibrium is where we are. 0 homogeneous equilibrium or the extinction homogeneous equilibrium. Let's say I take one grid and put some population here, right? Okay. Now what will happen is the question now. So your argument is the following, which is that this grid will try to reach carrying capacity, right? This seeded grid will try to reach the carrying capacity. And as it's reaching, its numbers are increasing. Is that what you're saying?
Yes.
And at the same time, it is now diffusing to all other locations nearby, right?
Yes.
It's located diffusing everywhere. And when that happens, you're also seeding the neighboring sites, neighboring grids. And now they will also begin to grow, and they will also again now seed the neighboring sites, right? Is that what you're saying?
Yes.
Okay. But there is also a loss back to the original focal cell. Okay. So the question is that, there is a growth here, in the focal cell where you initially began the seeding. Let's call that seeding, or the perturbation you made, that begins to grow. Now, if your argument is right, that growth will lead to diffusion, and that diffusion will lead to growth everywhere nearby, that in turn diffuses, and therefore now every grid cell, if you think in a discrete way, will reach carrying capacity. That's one possible argument. Okay, let me just provide a small counter argument. Okay, which is that there is a trade-off between growth that is happening in a grid and a diffusion. If the diffusion happens too fast, the growth cannot compensate it. So therefore, maybe it's possible that although the original system was unstable, that might actually now become stable. Okay. So there might be some trade-off between growth and diffusion. Is one possible argument one can make. Okay. I'm not saying I'm right. I'm not saying you're wrong. I'm just telling there is a potential trade-off. Okay. And what we will do today is to see how this trade-off actually happens. Okay. Any other questions? Any other comments before I go forward?
So if there is a growth and diffusion has a more influence on spreading it up and not getting it to get to the carrying capacity. So what happened to that numbers that they increased? Because they got diffused, they should be somewhere, right?
They might die off there where they go, because there is both birth and death happening.
Okay. Yes.
Okay, good. So let's see. By the way, your argument is correct, but let's just make sure we mathematically and very clearly or computationally show it. Okay, but just to be clear, your argument is actually correct. What you say will happen, but what I say can also happen. Okay, so the question to ask is, when will each of these arguments can happen? Okay. Any other questions before I move forward?
So it is a scale of the reaction diffusion and the diffusion reaction term and the diffusion term that's matters here.
Exactly. That's precisely. Is there a trade-off? Okay, between local growth and the spreading rate of diffusion. Okay. Okay, that's the basic idea. Yes, is there a trade-off? You will see that indeed there is in some cases, and exactly when it happens is what we would like to understand. Okay. Okay. So let's now try to understand again. Let's now go back. How do we do stability analysis? Let's see how much we can do mathematically. And when we run out of all of our mathematical abilities, we will resort to simulations. Okay. So you remember how we did stability analysis in the previous course. The basic idea was that we know there are no equilibrium. Let's call them n star. And then we make a perturbation, right? Sorry. We make a perturbation. Let's do the same, the same principle, introduce perturbations. So let's say n of x, value of population density as x, is we start with the equilibrium value n star. And then what do? We introduce a perturbation. Here is the thing, in the mean field model, Okay, by the way, just to be clear, if somebody hasn't still watched the previous lecture, when I say mean field model, I mean models that ignore space, like the simple ODE model, simple ordinary differential equation models, where we only look at the average values, where we ignore the entire space. Okay. So when we did the mean field model, we made a perturbation, but here because of space, there is a new complexity, which is that the perturbation I do is a function of space. In fact, the example that I don't know who mentioned this example, I don't know, where you make a perturbation, introduce some individuals in some part of the world, right? That means that everywhere else you made no perturbation, only in some location you made a perturbation, right? Which means the perturbation can depend on X. Okay, so we have to consider perturbation in the more general way now, and we need to now see what happens to this. Does this grow or decay, right? If this decays, we say it is n star is a stable equilibrium. Okay, so now let us go back to this equation, the general equation. Oh, I haven't done the general equation. Looking at the general equation, which is dou n by dou t is equal to f of n plus diffusion del square of n. Okay, so for each of the term here, let us plug this. For the left hand side, what is it? D by dou t of n star plus n of x. Okay, now of course this n of x will depend on time. So this was a time t is equal to 0, right? So this perturbation was introduced at time t is equal to 0. Some arbitrary time unit, which I am saying is 0. Okay, so that's the left hand side. The first term is a constant, right? So this percent becomes 0. So the left hand side becomes how the perturbation that we have introduced changes with time. Okay, not the overall density anymore. It's just a perturbation, how the perturbation is changed with time. Okay, what about the RHS? RHS has two terms. Let's do one by one. Okay, let's do f of n. What is f of n? F of n star plus this perturbation. Again, let us use our fantastic sort of tool we have, which is that of Taylor series. Okay, so we write this as the first, n of x is a small term. So therefore, I'm going to expand this function around n star. Okay, so we have f of n star plus the perturbation is n of x, dou of f by dou of n at n star. Okay, n square of x, dou of f by dou of n. Now it's also n square. Okay, again computed at the equilibrium and then so on. Okay, and let us keep only the first two terms. Okay, what is this term? What is f of n star? That is 0 because n star is in equilibrium. Okay, so this term we will ignore because it's a higher order term. Let's keep only the highest order term, and therefore we get this is equal to n of x, the perturbation itself, and whatever the slope of the f at n. So we have come across this in the past. Let's call this alpha. Okay, and we already know that in the mean field model, if alpha was greater than 0, you have an unstable equilibrium. If alpha is less than 0, you have a stable equilibrium. Okay, and we'll ignore the rest of the term. Okay, so that we have done this term now. We have analyzed this term now. Let us analyze the last term, which is the diffusion term. V del square of n star plus n. Okay, again, del square applied to the first term is 0, right? Del square applied to second term means basically it's a diffusion of the perturbation we have made. Okay, so now putting all the terms together, what we have is as an equation that determines how the perturbations are growing in space and time. So this is the at each location x, how is the perturbation changing over time? That's given by alpha times nx plus d okay. So this is how the perturbation grows in space and time. From equilibrium. Okay. Any questions on the mathematics so far? Okay. Have again had the same problem. I have no idea why this happens. I'll have to close the window again. Okay. Any questions on the mathematics part so far?
So in the RHS first term, that shouldn't that be alpha n alpha eta xt?
Yes, you're right. Thank you.
I just thought I missed a time dependence.
Thank you very much. Okay. Any other questions? In the mean field model, sign of alpha would have told us the stability. The question is now, will the diffusion change it in any way? Okay, that's something not very clear. Why is it so? So let's take a specific location. Let's say if alpha was negative, right? That means that locally, because of this term, there's a decay, right? But now, what about if there's an over? No, but this is a positive term, right? Diffusion is always a positive term, right? Okay. I mean, not necessarily always, it depends on the concentration differences. But what if the local decay, because alpha is negative, is compensated by the diffusion from neighboring sites? So is it possible that a mean field stable become unstable because of diffusion? We can ask this question. We can also opposite. We can think about the opposite. Opposite now is a bit harder. Now, locally it might be unstable, alpha is positive. But the question is, will diffusion somehow take it away? Can you spread away so fast and somehow can become a negative term? Okay, and therefore, although locally unstable, diffusion can make it stable. So one can argue both ways. It's a trade-off between the local growth and the diffusion that I mentioned. Is it evident from the equation now? The trade-off? Okay, so now what do we do? So let's again, consider a simple scenario. This is just for intuitive purposes. Consider a scenario we already know. Okay, so just like we considered homogeneous equilibrium, can we consider homogeneous, what am I going to say? Perturbation. Let's try to understand what happens in this case. So what's the homogeneous perturbation? So think of the fact that I have now started everywhere in the space with carrying capacity, right? That we know is an equilibrium. Okay, now one possible perturbation is I turn one of the locations, a very small part of the landscape, to a value away from K. That would be a local perturbation. Okay, only one place has undergone the perturbation. But what if I make every location perturbed by exact same amount? Okay, which means that the nx, which was the perturbation, right, at time t is equal to 0, right? Let's say it was some n0 for all x. So this would be homogeneous perturbation, right? So N0 can be positive or negative. Okay. What happens? Can we try to understand what happens in this case, at least from the equation now?
It'll reach carrying capacity, sir, also.
Okay, in this case. No, why? Because if I make a homogeneous perturbation, this means that the corresponding diffusion term, right, becomes 0, right? So which means that the dynamics of perturbation is governed only by this equation now, at all locations. Diffusion term plays no role, right? So in such a case, we can say that local stability, right, as determined by mean field model, right? Holds true in the reaction diffusion equation 2. Do you all agree with this? Of course, in some sense, this is very trivial. So by considering homogeneous equilibrium and then a homogeneous perturbation, I have practically made the diffusion term redundant in all of the calculations, right? So in a sense, this is a very trivial scenario, right? So in some sense, this is a trivial outcome. Okay. Because I have effectively eliminated not effectively, but basically eliminated the role of diffusion entirely in the dynamics. So therefore, whatever we had in the mean field model will continue to hold. Okay. So therefore, the interesting case is when the perturbation is non-homogeneous. Okay. So which means that we have to go back to this equation, somehow analyze this. Okay. So this is precisely why I asked you to read up something about what did I say? I asked you to read about Fourier transforms. So please do that before Monday, because in Monday's class I will be using it. Okay, so that will help us analyze the stability of the perturbations, even when the perturbations are not homogeneous. Okay, so how do we do that? I'll leave it to Monday. But today, what we will do is analyze this scenario in entirely numerical. So let's try to analyze these scenarios. Okay. So also let's think of what are all the useful analysis one can do. Numerical stability analysis for reaction diffusion equations. Okay. So let's think of scenarios that are important. Okay. So what are the simple scenarios you can think of? The first scenario is that start with Fisher-Kolmogorov equations. Okay. So Fk is a equation or model, which is basically the logistic model with diffusion. Okay. And then what we do is that we start with a homogeneous extinction equilibrium. And then what do we do? So think of it as a scenario where there is a landscape which doesn't have one specific species of your interest. Okay, and you know that if you have the species in a mean field setting, it follows the logistic model, and now of course you also have diffusion in it. So what is a perturbation that you will consider? Introduce this species, right? This population in some corner. Introduce a small density at some location. The question is, does this perturbation grow or decay? Okay. So this is one scenario, right? Is it clear to everyone what scenario you should try? Does it make a sense? Now, biological context where this could be could make sense is ranges quite a lot. Imagine that there is a species that had gone extinct on a location where it was originally present. Okay, now we have introduced a small number of them in some corner or some part of the landscape. The question is it going to grow or is it going to decay? That's one scenario. Another scenario could be there is an invasive species that has landed in a new landscape. Okay, because it has landed in the new landscape, it has no natural predators, it has no natural competition, which it has a massive advantage, which means R is positive and it has some K. Okay, so it has just been introduced in some location now. So now how does this spread? And one can ask the same question in the context of evolution, where you have a new, they say, think of a a locus with two alleles. Let's say one allele is currently dominant, or fully present as a fixation. However, a new mutation introduces other allele. So you want to understand, maybe that a new allele has a selective advantage. Okay, and now the question is, how does it spread in space? Okay, so these are a simple various scenario: invasion, mutation selection, and introduction of a species in the original landscapes. So these are all the various scenarios where you can think such a thing happens, because the introduction is not uniform, right? Introduction happens only in some location. So the question is, how does it spread? Does it spread? Is there a minimum number I need to introduce for it to spread? Is there some optimum locations where it is more likely to spread? So we can begin to ask all these type of questions, right? Okay. Any questions on this scenario? So what would be a natural scenario B? That is an extension of what I have just said.
Everything's at K.
Exactly, yeah. So you start with the homogeneous equilibrium at carrying capacity, and then introduce a perturbation. Okay. Which could, be greater than K, which could also reduce, and then ask the same question. Okay, same question. Okay. Okay, that's one model we can understand. What could be an alternative model to look at? So now there are, as we studied, yeah, go ahead. Yeah.
The perturbation more than K, or is the perturbation making the population less than K and more than K?
Yeah, I should have been clear. Sorry. So perturbation both greater than 0 and less than 0. Okay. So which will in turn make it n greater than K or less than K. Okay. So whereas in the previous case, perturbation can only be positive. Okay. So this is one simple scenario. Okay, this I will actually show you. Okay, this I will show you. And to do this, we need to have, what do we need to have? So I'll come back to second scenario later. So I will now introduce. How do we go about this? And this requires us to simulate, right? So this now requires us to, oh, very funny name. Numerical integration of P, T, E. By the way, this kind of equations are also called partial differential equation. And in this case, of course, we're dealing with reaction diffusion equations. Okay. Okay. So now how do we do? So let us first remember, how did we do numerical integration of the mean field modeling? So what did we do? We wrote this as n of t plus delta t minus n of t divided by delta t is equal to f of n. Approximate, of course. And therefore, what we have is, so we can calculate what will be the population size at a future time step given again, this is an approximate. Okay. The current population density by iteratively, okay, applying this simple numerical rule. Okay. Of course, as we know, there are many better methods. So this is very crude numerical integration method, also called the Euler's method. Okay. Euler's really first order method. Okay. There's also an Euler second order method. Then you have RK fourth order method and so on. So we can stick to this to make our life easy. Okay. This is how we did. Okay. And then one sort of rule of thumb we had was, we know what is the sort of the rate of change of the system. We have some value alpha. So what we tried to ensure was the delta t was much less than 1 over alpha. Okay. So 1 over alpha is a time scale. We need to make sure that not only it is less than 1, we must also make sure that the delta t is much less than the correlation time. Alpha is also called the correlation time. We will come to that later. But the time scale, time the system takes to recover to the equilibrium. Okay, the same problem. We have to close this and open again. Okay, am I sharing the right screen? Okay. So delta t is also less than 1 over alpha. Okay. So this was the sort of broad rule of thumb we used. So what about reaction diffusion equation? So we again sort of follow the same principle. The left hand side we write down the exact same way. Okay. So except that now we have space, so we have to do it carefully. So let me show it for 1 dimension, but the same idea holds also true for 2 dimensions. Okay. So what is the left hand side? It's n at location x. We want to, so basically there is some rate of change at location x that is given by this. Okay, now we approximate that as, we have, of course, it's all approximation, right? Okay, now, of course, if we have the exact values. Now, what about the diffusion? The diffusion derivative can also be discretized in the following way, which is d n x plus delta x comma t minus 2 n x t plus x minus delta x t divided by delta x square. Is it right? Or is delta x? It is delta x square, no, because the second derivative, right? So the idea, how did I arrive at this? You basically find the difference between the slope itself, okay, slope it, and then take and divide by delta x, and then the slope in turn will have one delta x in the denominator. Okay, so this is how we can discretize. So now what you basically do is, as you can see, this depends on time, this depends on time, this depends on time, all these times are the current time t. Whereas what you have on the left side is future time minus the current time. So I will just take all the current times to right hand side at location x. Okay, and then therefore we now have an approximate estimate of what will be the value in the future. Okay, so at location x, what's the future value? The current value times delta t times the local rate of change. Always think of what each term means. Okay, it's delta t times the local rate of change, that gives me the local increment, and then there is an increment because of the diffusion. Okay, and what is important to note here is that the value at x depends values at two nearby locations, x plus delta x and x minus delta x. If you also had x and y terms here, so you would have had another term of this type, but with y. Is that fine with everyone? So if they were dealing with 2 dimensions, there will be a diffusion from the x direction, there will be a diffusion from the y direction. So you will add up 2 terms. Okay, so this is the rule of thumb for, this is the approximation, the basic approximation for numerically simulating diffusion equation. But there are 2 important points to note. So really simulating so numerically integrating. So usually the word simulation is used when we have stochastic variables, numerical integration or numerical. Of course. What about that? How achieve is because do we properly obtain solution to any of those? Let me just not only should this
Sir, your voice has been breaking for the last 1 minute.
delta t must also be less than delta x squared by 2v. Then achieve. So you should actually try simulations without doing this. Choose a large enough delta t. You will find that you will very nicely find a lot of negative values of n. We also find n is equal to ridicule. We can't hear you in the last. Are you still able to not hear me?
Your voice is breaking a lot.
Really, really choppy.
Hello? Hello?
Your voice isn't clear from the last 2 minutes. Hello?
Hello? Can you hear me? Can somebody speak?
We can, but it's still really choppy.
So it looks like you are unable to hear me clearly. I don't know what I can do. Okay. ಮಾರಿಯಾ ಅವ್ರನ್ನ ಮಾತಾಡ್ತೀರಾ ಅವ್ರೇನೋ ಕೇಳ್ತಾ ಇದ್ದಾರೆ ಮಾರಿಯಾ ಠಾಕರ್ ಅವ್ರನ್ನ ಹೋಗಿ ಕೇಳಿ ಅವ್ರೇನೋ ಕೇಳ್ತಾ ಇದ್ದಾರೆ ಅವ್ರು ಮೆಸೇಜ್ ಮಾಡಿದ್ರು ನನಗೆ ಅವ್ರ ಜೊತೆ ಮಾತಾಡಿ ಮಾರಿಯಾ ಠಾಕರ್ ಇಲ್ಲ ನೀವು ಹೋಗಿ ಮಾತಾಡಿ ಹಾ ಹಾಯ್ ಕ್ಯಾನ್ ಯು ಹಿಯರ್ ಮಿ ನೌ ಇಲ್ವಾ
Yes.
ಹಲೋ
Yes, we can hear.
can you guys see, is it better now?
Yes.
I've just changed the network. I am hoping that it's better now. Okay, so I'll share the screen again. Luckily I have come to the end of what I wanted to say, but I do want to show one thing, okay, before I stop. Okay, are you able to see now?
Yes.
Are you able to hear me now?
Yes.
Yes.
Okay, so basically this is the what I have in the box is the numerical integration scheme for the reaction diffusion equation. So the first part, the first two terms are exactly same as what you had for the mean field model, and this is the diffusion term. And what is interesting about diffusion term is that the current location changes depend also on the two nearest neighbors. Is it clear? Okay, and then if you had two dimensions, it would also depend on the two nearest neighbor in the other direction, the y direction. Okay, and so on and so forth for higher dimensions. So this is the numerical scheme for diffusion, reaction diffusion equation. And now you have to choose delta x and delta t small enough, right, for the derivative approximation to hold true. Clearly delta t has to be very small. And what is important to note here is that the delta t has to be less than delta x squared by 2d. If you don't do this, you won't achieve numerical stability of your solutions. Is this point clear? I'm not giving you any reasons, but I'm just stating a matter of fact here. And this is something that's usually covered in numerical analysis kind of courses. So when you're doing simulation, this must be ensured. Is that fine? And usually what I do, I'll tell you the strategy that I use. I use delta x is equal to 1. Okay, then I know the diffusion value, and I will get the maximum delta t I can have. I will choose, and then I will calculate delta maximum, that is given by 1 by 2d. And then what I do is that I choose delta t is equal to 1 by sort of 100, at least 10, but maybe 100 of this delta t. Okay, we choose this. So this will ensure numerical stability. Do all of you understand what is meant by numerical stability of solutions? So this may not be clear to you. It's totally fine. If you have never come across the idea of numerical stabilities, it's totally fine. I can tell you broadly, the idea is that, we have an equation, right? It has, let's say, some solution. Okay. Now we don't know what that solution is analytically. We know there has to be some solution. Let's say we have some reasons to believe we have solution. I'm now approximating, right? Whenever I'm converting derivatives to discrete form, I'm making a lot of approximations. So therefore, the resulting equation is only an approximation of the original differential equation. But to ensure that the numerical solution of the approximation is close enough to the actual solution of the differential equation, you have to ensure that these delta x and delta t's are not too large. And in this case, they have to follow this criterion. Okay. Is that explanation sufficient for now?
Could you explain what's delta Tm again?
Delta t is the maximum value that the delta, so basically this inequality, right? Delta t must be much less than this value, right?
Okay.
So I'm computing delta max, delta t max, which is basically given by this, okay?
Okay.
For delta x is equal to 1, it will be 1 over 2d. And what I then do is I assume that delta t is equal to 1/100th of the delta t max. That way I'm assured of numerical stability. If you take delta t is equal to delta t max, then you will be assured of numerical instability. Okay, you will get arbitrary solutions which are not right at all. You'll get crazy values. Try it out actually. So I will stop here this presentation. I will now show you the R code.
Sorry, I just had one question. How is, like, I understand the concept of numerical stability, that you're trying to basically assay the stability using a kind of time evolution that you can do computationally. But what exactly should we be looking for? Like, what exactly indicates that this is a numerically stable system? So if whatever your RHS nx t plus delta t is less than 0, that indicate, like, what exactly are we looking for as far as a result is concerned, indicating the numerical stability?
I don't understand your question.
So essentially what we've done is we've started with d n by dt.
Yeah.
And we've sort of re-expressed it in the form of like in terms of nx dx and delta x and t delta t. So what should we be looking for? Like when we're solving this equation and doing some iterations, how do we kind of figure out that this is a numerically stable system? Like we have,
are you asking a general question for any differential equation, or are you asking a question for reaction diffusion equation?
I mean, it's not very equation specific in particular, but if I have something of this form, a numerical integration scheme or whatever, how do I sort of figure out that, like, I may run some iterations on it and I may find some relation, but how do I determine from that whether it is stable or not?
So there are standard techniques to do it. I will maybe show one such example after I show this. Is that okay? Because that may not be of interest to everyone. I can just discuss that with you separately or at the end of this, after showing the code. Is that fine? Because numerical stability is not something that's I'm going to cover in depth anyway. I'm going to assume that we will read up for a given type of equation what is the right method to use, and we will just use it. This is not a method for numerical solution anyway. So I'm going to bypass your question for the time being. Is that fine? So basically, if you have a reaction diffusion equation, there is somebody has proved that delta t has to be less than this condition, so we will follow it. For some other PDE, somebody has established some other condition, we will follow it. That's the strategy we will do for this course. Okay, is that fine? I don't know if that's satisfactory, but for the purpose of this course, that is sufficient. But I can discuss that separately with you. Okay. What is the principle behind it? I can discuss that separately. Okay. So what I have now is a R code where I have already implemented the numerical scheme. I'll just take you through this. I think I wrote this code back in 2014 or so. Luckily, I found it. I didn't have to write again. I made some few modifications. Okay. So I'm going to upload this on the canvas if I already haven't done. So what I'm now going to do is just quickly take you over. So there's a library I'm going to use. This is a very useful library for plotting. See, when we have a non-spatial model, I can just plot population density on the y-axis. My time axis will be x-axis, right? So I have some time size. But now what you have is there is a population density at every location in space. How do I visualize it? Right. So this is going to be very useful, this package. So now let me declare a whole bunch of functions. So the first function is now something very well known to you. This is the deterministic growth rate function, or the reaction function, the way we have logistic growth Rx into 1 minus x. I'm sorry for using x. I should have probably used some other notation here, maybe n or so on and so forth. But I don't want to change it now and introduce some errors. Okay. So because so far we have been using x to mean space, right? So I'm sorry that I have used x here. So think of it x as the population density. So Rx into 1 minus x by k, that logistic model. This term again is something all of you know, this is Holling's functional 3 response. So if we set h is equal to 0, we have basically logistic model. That's what I will show you today. Just h is equal to 0. Okay, here is a very interesting thing called periodic boundary condition. See, all along, when we have been talking about the space, I haven't really told you what is the boundary, right? In real world, there are boundaries of various types. Okay. For example, if you are thinking of a national park, it is bounded by various, landscape features. You suddenly, in India, for example, if you go from the national parks to the edges, you suddenly find agricultural fields, right? So the environment experienced by organisms are dramatically different across the boundary. Okay. So the nature of boundary becomes important in a number of scenarios. What we do in the simplest theoretical model is called a periodic boundary condition, which is a really funny and elegant concept at the same time. So what is a periodic boundary condition? So for that, I will have to share a different window. I'll share this again. Are you able to hear me well now? There is no chopping of the audio.
Yes.
Okay, great. So periodic boundaries are really amazing. Have you heard of, how many of you have heard of periodic boundary conditions? No one. Okay, great. That makes it even more interesting. Okay. So the idea of periodic boundary condition is this. Okay. So what we are, there is a whole massive landscape. Okay. But what we are simulating in our equations is a very small landscape. That's the premise. Okay. So what I have this, what I'm simulating is this smaller part of the much bigger landscape, and then I'm discretizing it in space where each grid is of the size delta x. Okay. Now, how will the boundary look like? So the idea of the periodic boundary condition is that if I'm exiting this, an individual who will randomly walk away from here, where will that guy go? That guy hops back from here. Okay. On the other hand, someone who goes out of this boundary area that I am simulating in this direction comes back in this direction. Okay. What that basically means is effectively that so let's think of this focal cell, right? Who are all the neighbors? So neighbors are all this. 4 neighbors, 4 nearest neighbors. Okay. Now let's think of, this as the focal grid. Who are all the neighbors? This is obvious. Nearest neighbor, another nearest neighbor, another nearest neighbor. But my simulation is ending here. So periodic boundary condition means that the neighbor of this guy is actually this. Okay, and I can give one more example. Let's take this focal cell. The 3 neighbors are fairly clear, and the other neighbor is actually here. Is that clear now? So such a sort of a periodic, such a condition is called periodic boundary condition. Topologically, a periodic boundary condition is equal to torus. If the entire ecological phenomenon is happening on a torus or a donut kind of a shaped world. So basically, what does this mean? You can think of this edge being same as this edge, right? That means you should think of folding and joining these 2 edges. So what you now have is think of a paper. I wish I had a paper with me to show you this with my video. I'll just show it. It's not going to work. I'll just show it anyway. So what the periodic boundary condition means is, can you see my video now? Okay. So this is the, let's say imagine this is the landscape we are simulating. As I told you, the somebody who hops out of this actually will come back here, right? That means population diffusing out of this actually comes back here. That effectively means that what I have is that I have folded these two edges like this, right? So therefore, movement along one edge now becomes this edge. How about this now? Somebody going along this edge comes out on this edge, right? That is same as saying we will fold this space in this way. I can't do this, okay? So now if I do this really, really well, what will I get? I'll basically get a, something like a torus, right? Basically a donut. Okay, this is what we will get. Well, this is a really, really weird ecological space to be in. Okay, but nevertheless, this is a very good, this approximation called this condition called periodic boundary condition is very useful for simulating very large areas. And this is a technique used in physics. Okay, and why do physicists use this? Because physicists often work with, let's say, lattices, right? Real physical objects, lattices. And in lattices, there are 10 to the power of 3 particles, okay? 10 to the power of 23 kind of particles. And what you are simulating is often a really small number, few thousands, maybe few millions, right? This is an approximation that makes perfect sense there. It makes less and less sense when you come to small ecological landscapes. There we do use different boundary conditions, but for the sake of simplicity, we will continue to use periodic boundary conditions for the rest of our course to a large part. Okay. So this function, yeah, go ahead, please. Yeah.
Is a large grid size a necessity? Like I've been using this in my ABM models. Like, should it be very large? Like, can the grid size be small also?
So the right way to think about this is, you are trying to simulate a really large system, okay, and you are only simulating a small part of it.
Okay.
Okay, but the small part must still not be very small. It must still be a sufficiently large landscape. Okay. For example, if it is 2 by 2, that's just ridiculously small. Okay, 100 by 100 may be okay.
Okay.
So that's where you are simulating. Okay. Okay. So this part does what, this makes sure that, say, basically the way this entire code runs is we now have state population density stored in the form of an array, a 2-dimensional array. Okay.
Sir,
So I hope, yeah, sure.
So you told us about a torus. Does a sphere represent anything, any kind of boundary condition which is useful to us?
Sphere, I mean, it's a 3-dimensional surface. It doesn't represent a boundary condition per se, right? So for, yeah, I mean, I don't think it becomes an approximation for something. I don't know. A ring is a ring. Basically, is imagine you have 1-dimensional landscape, and if you now impose a periodic boundary condition, it becomes a ring, right? Yeah. 2D periodic becomes a torus. 3D periodic, God knows, whatever the hyper torus it is. Nobody can visualize it.
Yeah.
Okay. Okay. So this this implements the periodic boundary condition. It basically copies. It creates 2 extra arrays in your landscape and then stores the values there. Don't worry how it's done. You should read it when you have time. I won't explain that in detail. Okay. And what the next function does an initialization. What should different locations on the landscape, what are the values going to be from? That's what this function does. Basically, think of this landscape, it's stored in this array called X array. Okay. X array, I goes from 2 to n plus 1, J goes from 2 to n plus 1. Okay. That means that the size of the array is n by n. Okay. N in X dimension, n in Y dimension. Okay. and then this function gives some initial values. So specifically, it gives 0 for all values, okay, in this specific case. Okay, I think it gives a non-zero value for only one location. Only one grid has a value of k. Every other grid has a value of 0. So this is like introduction of a species in one location in the landscape. So in fact, I'm introducing at n by 2 and n by 2, which is the center of the entire spatial grid. Okay, that's what we are doing here. So this is the initializing the space. This function does that. Okay, and then this function implements the diffusion. Okay, I showed you this diffusion term, right? X, n at previous location, the right side location, left side location, and then subtract it from the current location. This is the diffusion in the x direction, diffusion in the y direction. This gives me the total diffusion. Okay, so there are basically 3 or 4 different functions that defines the local growth rate, that defines how to make the area periodic, that initializes your landscape, and then that diffuses the landscape as the growth happens. Okay. Now I have defined various parameter values. R is equal to K, carrying capacity is 1. There is no harvesting rate in the beginning at all. So therefore, these two doesn't even make sense. So I have assumed that the diffusion coefficient is 1, the capital D. I have assumed it to be 1. Okay. And now this is the numerical integration value. So I'm considering a n50 by 50 landscape. Okay. I'm considering that grids are of the size 1 by 1 unit, delta x is 1 unit, and I'm assuming that delta t is 0.1. Okay, so you remember that have to choose the delta t is less than delta x square by 2d. Okay, so delta x square will be 1 because delta x is 1, d will be 1, so 2d is 2, so delta t must be less than 0.5. So I have chosen delta t to be 0.1. I haven't actually chosen delta tm by 100, by the way. I have actually chosen a much larger value, but still it works well. Okay, but if you do choose delta t is equal to 0.5 in this case, you should try it out on your own. Everything blows up. Okay, so here I have just defined all these arrays, and then we will now begin to implement. Okay, so current population is a matrix. It's an n by 2 plus n by 2 matrix. Why have I chosen n by 2 plus n by 2 matrix instead of n by n? Does anyone know? Does anyone understand this? The reason is that what I have done is that we are interested in the n by n matrix, but I have added extra rows and columns across. Think of them as extra patching or padding in the numerical solution scheme, so that I can do the periodic boundary condition in an efficient way. Okay, so if you don't understand, it's okay. Don't bother too much right now. And then I have defined past value, current value, and something for the plotting. Okay, so we have done all these things. I initialize the population using the initialization function, and then there are a few manipulations I do. So this is the image.plot is the one that will plot the 2-dimensional surface. Okay, and then we do the integration here, and then the same principles of integration, and then we plot them. Okay, so all is in place. We just now run the code. Okay, so remember what I have done. We are basically running a logistic model with diffusion. Everywhere there is 0, there is no population density, but exactly at the center of the landscape, I have planted a lot of individuals. Are you able to see? So note the scale of the colors. So everywhere it's blue, meaning everywhere it's 0. Can somebody confirm that you're able to see this?
Yes, we can see.
Thank you. So what's happening? Can somebody describe what happened?
We could notice the spillover from the left side, enter from the right side. And
okay, that's the last part, but from the initial parts, initial stages of the simulation, what happened?
It slowly spread out from the center towards the edges.
Okay, so what I had done was I had initially planted K, population density K in the 1 pixel, only in the one site of the 50 by 50. 50 by 50 means there are 2,500 grid cells, okay, of which only one cell had a value of population density of 10. Every other site had a population density of 0. Okay, that was the initial condition. Okay. So that's, basically you can see everywhere it has now reached value of K, right? K was 10. Okay. So I'll stop it again. I'll just run it again just for you to see. See what happened now? What happened to the brightness at the center initially?
It dropped.
It dropped. So I had put in K density at the center. Initially, what happened? It actually went down. Why did it go down?
Because of diffusion.
The diffusion. I told you about this trade-off between the spread and the local growth, right? Initially, it actually decayed, right? It actually decayed initially and it spread out. Okay. And then it grew back again in the center. See the trade-off that I mentioned, but somehow the initial trade-off was overcome eventually. And then everywhere in the center now you have a large population density and it's spreading all over the place. Okay, this I have seen again. I will stop. Now tell me, where do you want me to place? Let's now go to this initialize space part of the code. Okay, tell me where shall I place? So initially I have put at the center. Okay, where shall I place it now? Which location shall I place? Shall I place it in some corner? And let's see what happens. Okay, let me make this 0. Okay, or maybe 2. Okay, so I have placed. I'm going to place it in some corner, middle but corner. Okay, but not in somewhere on the middle of the edge, middle of the one of the edges. I have placed it here. Were you able to see where I placed?
Yes.
Yes.
So you can also see the effect of periodic boundary conditions now. So because of the periodic boundary condition, does it really matter where I place the overall growth pattern? Does it really matter?
No.
Or it shouldn't matter at all, no? So because of the periodic boundary condition, I have ensured isotropic space. It's whole, all directions are identical. So although you're seeing it as two broken rings, but technically it's exactly same as what was happening in the previous simulation. Okay. So these are all the, you can see here, this is the front that is expanding. Okay. So Fisher or Kolmogorov, I forgot who now. One of them derived what should be the speed of this front. It's also called the invasion fronts. Okay. What is the speed of this front and how does it depend on the model parameters? Okay. So there are two parameters here. No, one is that of growth rate R, right? Other is that of the diffusion. He calculated how it depends on R and D. Okay. So I will share exactly his result. I don't remember right now. I'll maybe share on Monday. Okay. So he derived how the speed of the front depends on the diffusion constant and the local growth rate. Okay. So this is fine now. So I have shown you what I had to show. Any questions before I give you the work now? Any questions on what I have shown you? Okay, no questions. So now I will I'm uploading the code on Canvas now. This is the code that I just showed you.
Is the periodic boundary condition exactly a torus? Like, isn't there a stretching to make it a torus? Like, I'm not sure.
See, torus is a topological object. How much you stretch and bend is irrelevant.
Okay.
Are there any mathematicians in this audience? If they can confirm me. Okay. So I have uploaded this reaction diffusion code. Okay, it's called reaction underscore diffusion underscore 2dim.org. I have just uploaded it in the codes folder on the Canvas. Okay. So now let me explain what you will do. Okay. So let's go back. Scenarios. We discussed these scenarios, right? The first one I have shown you, at least, I have shown you the perturbation for this. Okay. So something you can just try, but that's not very important. I think you know what will happen very obviously now. Okay, now the second scenario I want you to look at is, maybe we could choose the harvesting model itself because we have studied that well in the class. Harvesting model. Okay. So what is the harvesting model? A mean field model looks like this. Okay. N dot is equal to Rn 1 minus n by k minus h n square by n0 square plus n square again. If I choose R is equal to 1, k is equal to 10. If I choose this, we will have this bistability in this model, which is if I plot n star as a function of h, we will find a pattern like this. This is k. It will look like this. Is it fine? And now I think this value is close to 2.6 approximately. I think this is close to around 1.5. Huh? Is that right? Does anyone remember these numbers? Approximately. I could be, think of it as approximate numbers. Okay. So here is the question for you. So what we have done is we have analyzed what happens for h equal to 0. Okay. The first thing you should do is to just go back and use the other code you had from last semester. I can upload that also, which calculates the bifurcation diagram for the harvesting model. Now you will know the exact values. Now choose various values of h. Here, 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 here. Okay. So now stick to this. Okay. Now for this, we know that 0 is an unstable equilibrium. 0 is of course unstable for throughout. Let's say now I start with this. And if I introduce a small element of k, what do you expect? If I'm here, and now consider the spatial model. Okay, of course, with space. Reaction diffusion. Okay. If I now introduce only at one site, k, what do you think will happen? So you have done a perturbation to the unstable 0 equilibrium. Analyze what happens. So in every case, start with this 0 equilibrium and introduce your perturbation. And I would like to see what do you find. Okay. So what is interesting is the following, right? You are imagine in this range. there are two equilibrium. Where will the population reach? Will it reach this one? Will it reach this one? What do you think will happen? So the interesting question to ask here is, what happens to perturbation in bistable region? Because there are two stable states. Where will this go? Now, of course, you already have some hints from your mean field model understanding, right? Now here, if I make a small perturbation, where do you expect to go in the mean field limit? Will you go to the lower branch or the upper branch?
Lower branch.
Lower branch, right? So small perturbation should lead to mean field branch. The lower branch. Whereas a perturbation that crosses this unstable equilibrium, if the initial perturbation was here, what do you expect in the mean field model? You expect to go to lower branch or the upper branch? Upper branch, right? If the perturbation was somewhere here, what do you expect?
Upper branch.
So we have chosen a value of h here, by the way. Value of h is here, but the initial value of the population is here. So we'll come back to the upper branch. But what if the perturbation was somewhere here? We will come to the lower branch, right? If you are here, you will come to the lower branch, so small perturbation. Now with space, you can ask the same question. How does the strength of perturbation, right? Strength of perturbation depend on affect, right, the final outcome. Is the question clear? So now here is my question. How do you define strength of perturbation? So remember that we wrote it this way, no? So perturbation was the n of x was some n star plus n of x. So, seems to put it happen again. Okay, so how do you define strength of perturbation, right? Now you have n of x, right? Now in the mean field model, the distance from the n star was sufficient to describe the strength of perturbation. Is it sufficient in the spatial system?
Does it also depend upon the diffusion coefficient?
Let's say we have fixed the diffusion coefficient.
You have to also account for the spatial distribution
Of what?
of the perturbation.
Very good. So basically, the example I showed you had, a perturbation only in one pixel, right? Okay. So now you have basically two parameters. One is that how many pixels are you perturbing? How many locations are you perturbing from the equilibrium? And then what is the value you are choosing for each of those grid points? So both of them matter. Okay, so your perturbation can be a single pixel, a single grid point, or a square, right? Square of size, maybe 5 by 5 or 10 by 10, whatever, right? And then value of n at those grids. Okay, so I would like you to investigate how this, given both by the area, number of pixels you choose to perturb and the value you choose, how these two will influence the final outcome. And is there anything interesting you find in the process? How do those two determine whether you go to this state or this state? So I would like you to just do a lot of numerical experiments and come up with something. Do you find something interesting in the process? Is that question clear?
We can also have independent perturbations, right?
Oh, spread all over the space, no?
Oh, yeah.
Yeah, you can also consider that. Yes, we can also consider, different perturbation types. That's totally fine. Yeah. Okay. Different perturbation geometries, right? So, one patch of some size, right? Or multiple patches of perturbation, or even random distribution. So you can try all of this. Huh? Okay, but if you are badly stuck and not clear, stick to one patch scenario only. Okay, but you vary the size of the patch as well as the strength of perturbation within each of the grids in the patch. Is this clear? And then I want to know, how does that affect your results? What's the sort of just some interesting message you find from these numerical experiments? Okay. Okay, so I will stop here. I will let you all start your work right now.